Hello, Mr. Colati here. Today we're going to be looking at Venn diagrams in detail. And this is one way, one diagram and solution strategy for solving probability problems. So here we just give you an idea. You know Venn diagrams, we've kind of introduced them. You've probably seen them in your life before, but here you have flour, egg, and milk, and when those overlap, they make, flour and egg makes pasta, milk and egg overlap to make omelet, but when all three overlap they make pancakes, which are delicious. So Venn diagram is a strategy for solving probability problems. What we do and what we're going to do is represent the set with a Venn diagram. The entire space is represented by a giant box called U, and then the event is represented by a circle, and we know that as A. A complement is the area outside the circle. And we'll show you that down here in an example. But first, today all of the things we're going to be discussing have to do with playing cards. So here is a set of 52 playing cards. It's a standard playing cards if you went to go play at a casino or if you wanted to play Crazy Eights with your friends. Maybe you know these, maybe you don't. Let me just give you a quick explanation. 52 cards. There are 4 suits. The suits are the kind of shapes or the depicted on each series of cards. So this shape is clubs, these are all hearts, aces, and diamonds. And for every suit, the cards range from 1 or ace all the way up to 10, then jack, queen, and king. So we have each of those repeating 4 times. So that's just kind of the backgrounder on what we're going to be doing today. So here I'll just write out. Again, maybe some of you guys play Uno all the time and you don't know your cards. Hearts, this is spades. Some of you guys are studying French, right? Do you know how to say these things in French? Because that would be useful when you go to France and you want to play cards with someone. Okay, and oh sorry, I meant to write that this is called the A complement. Not A prime, it's A complement. And we'll see, I'll show you what these things are. So here's my first question. What is the probability of drawing a diamond? So the probability of A, we always call the event, it's the thing in bracket, and that A is a good name for this event, drawing a diamond. We saw in the previous lessons that this is the number of diamonds over the total number of elements in my sample space. A, event A is the drawing of a diamond. So if I shuffle all 52 cards and I randomly select a card, what's the chances I'm going to get a diamond? Well, how many diamond cards are there? The number of diamond cards. There are all of these down here. That's 13 of the set. How many cards are there in total? 52. So that's my probability. We already talked about this. If I wanted to represent this on a Venn diagram, so here's my Venn diagram, the flag of Japan for some of you, if you were to color it red. The box U is for the box. That represents all of the cards in my sample space, all 52. Event A, or circle A, is this event, which is diamonds. So if you have to think, this is all the diamonds. And how many cards are in this circle? 13 cards. Okay, and that's, that is linked, right? These two things are showing the same thing. We should just put a note that box U represents all 52 cards. And this circle represents all 13 diamonds. So you're going to get more comfortable with this kind of notation. Now, what is the probability of not drawing a diamond? So remember, I have 52 cards. I select a card. What's the chance that I don't get a diamond? Well, we call this the complement. The number of elements in a complement is all the cards that aren't diamonds. So it would be, you guys can figure this out, there would be 39. The way we got that is we took the number of elements in total, which is 52, and we subtracted all the elements that were that event. So we had 52 cards, 13 of them were diamonds, so therefore 39 of them are not diamonds. Therefore, the probability of a complement happening, that is of not selecting a diamond, is 39 over 52. I think I've said this before. It goes without saying, though, you don't need to reduce the probabilities. You can just leave them as fractions like this. That's fine. Don't stress about reducing. So there we go. That's how the Venn diagram, the basic Venn diagram works. That's what the complement is. There's a neat thing here that we should note, and this will come up later on, but the probability of A plus the probability of A complement is equal to 1. That is the probability of A, of A complement is equal to 1 minus the probability of A, right? And it makes sense. The probability here plus the probability of here, together they equal 1. That's all the probabilities. So I'm just going to make a note. Wow, and can you believe I'm going to scan this? It's going to live forever on the internet, and it looks horrible. Okay. Now, if I wanted to represent the complement on my Venn diagram, it would be here, right? If this is A, then this area here is A complement, which is the non-diamonds. And there are 39 cards here. That's the thing about the Venn diagram. 52 is the total, but I have to add 13 and 39 to get 52. Okay, let's continue. So now we're going to use this Venn diagram to start defining some different types of sets and some different probability events. The first thing we're going to look at is mutually exclusive events. These are events that cannot occur simultaneously. So for example, let's go back to the cards. A card can either be a heart or a diamond. It cannot be both. So we say that hearts and diamonds are mutually exclusive. If I had to draw this Venn diagram, I would have my event A are the diamonds. I have 13 cards that are diamonds. And event V would be hearts. I have 13 cards that are hearts. Notice that the circles do not overlap because they have no shared elements. Circles do not overlap. How many cards are outside are not diamonds or hearts? Well, if there's 13 here, 13 here, it's 26. So there are 26 cards that are outside that are neither. How do you remember this? Mutually exclusive. I mean, you might have heard the term outside of math class. I always think like, you know, back in my parents' age, if you were dating someone, you would say you were exclusive. So you weren't seeing anybody else. So that, you know, you might think of that here, like they're exclusive. They don't overlap at all. They just are by themselves. This couple does not interact with this couple. Whichever way you want to look at it, you need to remember that mutually exclusive means that you can't have both properties. Okay, let's turn the page. Now it follows from mutually exclusive event. The other definition would be non-mutually exclusive events. These are then events that can occur at the same time. For example, diamonds and face cards are not mutually exclusive. Go back to my cards here. A card can be a diamond or a face card, but it can also be both, right? There are some cards that are both diamonds and face cards. So those two properties, those two events are not mutually exclusive. Let me show that in the diagram here. So I have my diamonds and my face cards. Now, there are 13 diamonds in total. There are 13 diamonds, right? Of these, 3 are face cards. So then, actually, in the diamond circle, there are only 10 in this circle, right? This part of the Venn diagram are only diamonds. And then there are 3 cards that are part of both circles. Those are the Jack, Queen, and King of diamonds. They are both diamonds and face cards. Now over here we have a similar issue. There are how many face cards? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 face cards. And of these, 3 are diamonds. So then it follows that there would be 9 cards that are only face cards, and again those 3 that are part of both sets. How many cards remaining? Well, so I have 10, 13, 21 cards in the circles. So outside the circles, I have 30 cards. This is kind of a tricky calculation, right? The remaining cards, the cards that have not been considered, well, it was 52 in total. Then you take away 10, you take away 3, you take away 9, and you're left with 30. So I took away all these values. Okay, we've defined mutually exclusive and non-mutually exclusive. Now we need to define some of the logic that we use with Venn diagrams. The first thing is the union of events. So the union of set A and set B contains all elements belonging to set A or set B. And the or is important. I'll also write or both. So when I say union, I'm saying you're talking about something that is in set A or set B or in both. It can be in either one of these 3 spots. The or I really emphasize because you'll see this language, especially in the non-IB program, they use or a lot. And in if you're doing computer programming and some logic, this will, or and AND gates will come up in logic for computer programming. So you might be familiar with it from there. So for example, if I'm going to go down to this question here. What is the probability of selecting an even numbered card or a red card? Well, even numbered or a red card, that or indicates that we're talking about a union. The way we write a union is kind of this U like this. So I'm going to write, actually I think I'm going to draw it up here first. So let's talk about these 2 events. The first event is an even numbered card. How many cards are even numbered? Well, one, 2, 3, 4, 5, right? 2, 4, 6, 8, 10. There's 5, 10, 15, 20 cards that are even numbered. But then I want to also know or the cards that are red. So my other event is the red cards. Now, of my even cards, 2, 4, 6, 8, 10, these are black, these are red, these are black, these are red. So 10 of them, 5 and 5, are red, 5 or 10 are not red. Right? So I have 10 even numbered cards that are not red, and 10 even numbered cards that are also red. Similarly, when I'm figuring this out, over here I go to red. I have how many? 13, 26 red cards. Of those, 10 are even. So I end up with 16 cards that are just red. So again, I've just made a non-mutually exclusive Venn diagram. 10 even cards are only even. 16 red cards are only red, but then 10 cards that are both even numbered and red. If you did the math, you'd find there are 16 cards that are not part of either. Because remember, the total here is 52. Okay, so when I say the union, I'm talking about you can be either even numbered or red or both. So I'm talking about all of these cards. So I'm just going to shade in the entire thing. The union here is both circles. So I'm going to write the union this, what I've just shaded, is the union of A or B. That's what we'd write in normal grade 12 data management. In IB, we tend to write with notation, so we write A union B. So this U is kind of like a big U. That's a union to unite two sets. So it's not like, it's like a big U, and it's used for set notation to combine these two. When I talk about unions, how do I remember this? Well, think about union, it's a marriage, right? So in set notation, or when we look at sets and we look at probability, this union is a marriage of event A and event B. They combine, you know, event A owns a house, event B owns a car, and so when they get married, now they both have the car and the house together. So now I can go down and answer this question. What is the probability of selecting an even numbered card or a red card? Well, that means I want to find the probability of A union B, the two things. To find that, I would have to count the number of elements in the union divided by the total number of elements. Well, there are 10 plus 10 is 20 plus 16. There are 36 elements in the union and 52 cards in total. I guess I should have shown that over here. NU is equal to 52. The number of elements in the union is just adding up these three numbers. So it's 10 plus 16, which is equal to 36. So that is union. Anytime you see or if you're talking about you know, a lot of possibilities, you end up with a union, and you calculate it. You can use a Venn diagram to help you. Okay, let's continue with our other kind of logic for this, for looking at events, which is intersection of events. So the intersection of set A and set B is the set where all elements are common to set A and set B. They must be part of both. So if you have, okay, let's look at this example here. What is the probability of selecting an odd numbered card and a club? So our two events are odd numbered and club. Okay, odd numbered oh, where's my page? It's over here. Odd numbered, similarly, we have, okay, ace, 3, 15, there are 5. Okay, so there are 5, 10, 15, 20 odd numbered cards. We'll call ace 1. So 1, 3, 5, 7, 9 times 4. So we get 20. How many of those are also clubs? Well, oh, just these 5, right? 1, 3, 5, 7, 9 are clubs. So we end up with 5 cards that are both odd and clubs. We have 15 then, to make 20, that are odd. And how many are clubs? Well, there are 13 clubs in total. 5 of them are also odd numbers, so how many are left over? 8 cards. This is an important distinction, right? Clubs, there are 13 in total. That's 5 plus 8. Okay. So if I'm talking about the intersection, that means I'm talking about the elements that are both odd numbered and club. They're part of both of these things. So that would just be this exclusive set in the middle. This is the intersection of A and B. Again, that's how you would write it in a regular grade 12 class, but in IB we use notation. We write A intersect B. So there, that's the upside down U, which means where A and B intersect, or where they overlap. If the union is a marriage, I always think of the intersection as an overlap. Where do they overlap? Or some some students say like, oh, it's like the child, right? Like if you have the two parents, they both give genes, and the child has some genes from both parents. Whatever. It's as long as you can distinguish between union and intersection. So if I ask you, what is the probability of selecting an odd numbered card and a club? Well, and immediately you should be thinking, oh, that's intersection. That means I have to have these two properties, which is very rare, right? This is our special cards that are both odd and a club. The probability of A intersect B is, well, the number of elements in A and B over the number of elements in U. Well, you can see right here there are 5 in that are part of both, and there are 52 in total. I'm going to write this here because this is going to come up again, but usually we can just write this answer. Don't get caught up in notation. So just, sometimes you're going to be asked for this question. You could just write 5 over 52. Don't worry too much about the notation, especially some of the more complicated problems. The notation tends to bog you down. All I'm interested in is the probability. And remember, you don't have to reduce this, although you can't reduce it. Okay, so there are all of our definitions: union, intersection, mutually exclusive, non-mutually exclusive. Now, I'd like to show you, before we do a long example, some of the more difficult ways that Venn diagrams seem like a pretty straightforward idea, but they can get a little bit confusing when you combine Venn diagrams and different complements. For example, can you shade the A intersect B complement? Well, this is a confusing thing. So first of all, intersect means where these things overlap, right? The and idea. So I need to take all the A's. So what helps with these questions is draw a little sketch off to the side. So let's look at these separately. So this is A. So A would be this, right? Would be all of this circle. So that would be A. And then what would be complement of B? Well, B is everything inside this circle. Complement of B is everything outside of this circle. So it's actually a lot. Like it's everything. It's partly the other circle. It's all of this space here. But it's not, it does not include this circle. Okay, so now this is A, this is B, complement. And I want to shade where I have not, or sorry, and where those overlap, the intersection. So where does this overlap with this? So imagine I had those old overhead projector pages. So I have this page with an area colored in, and I have this page with an area colored in. Where is that when I hold them up to the light on top of each other, what area is colored in for both? Well, it would be just this section of A, right? Like just I call it the crescent moon. Like it's like this bit here. Right, that's a nice way of saying only A and the complement of B. Okay, these are more difficult. I find these sometimes can be confusing for students. So let's do this again. A union, that's or, A complement union B. So let's again, helps I find sometimes to draw a little sketch off to the side. So this is A complement. So that would mean not A. So if this circle is A, then I'm talking about, when I talk about A complement, I'm talking about everything outside of A. So all of this. La 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 la. Okay, and then for B, well, that would be everything in the second circle. Okay, now we're talking about the union. That's the marriage, right? So that means I have this A complement marrying B, so they're combining all their possessions. So I get everything that A has plus everything that B has. So what I end up with is this massive amount of space. It's like everything. They own the world. Now you can just feel free to fast forward the video as I slowly shade this in. There we go, beautiful art. So that's what the A complement union B. Remember, the union is a marriage. It ends up being a lot more space we're talking about. Let's look at this one. This is, oh my goodness, A complement intersect or and B complement. So you guys, we've drawn this a few times now, but let's do it again. A complement and B complement. So A complement, oops, sorry, that wasn't great. A complement is everything that's not A. So it's everything outside of A. And B complement is everything that's not B. So it's everything outside of B. So when these two are, I want to look at the intersect, that means I want to look at where they overlap. Okay, so if you look at it, like A, this is not A, and then here this is not B, but there's no overlap here. So the only thing that overlaps this area is actually all this area around the two circles. So when we talk about this, I'm actually looking at this space here. There we go. Da, da, da. Okay, interesting. So A complement and B complement, we're actually talking about the area around the two. Finally, we have one more. This is a great one. A union B, and then the complement. So first of all, let's go back here. What does A union B mean? Well, A union B is the marriage of A and B. So it's all of A married with all of B. It's all, remember the house and the car, they combine them when they get married. So the complement of that is everything that's not in either. So it's actually the same as what we just drew. It's everything that's not A or B. Like that, great, beautiful. And so we actually find that these are the same thing, right? Like N A complement intersect B complement is actually equal to N A union B all complement. But I find sometimes when I'm unclear of the notation, which sometimes you will be, it helps to think of it this way, to draw little pictures, Venn diagrams to help you out. Okay, let's do one long example. And this is great because this is an example that is commonly on the IB exams, and they're actually not that challenging to do, but you just have to follow my strategy. So in a class of 30 students, 19 study physics, 17 study chemistry, and 15 study both. Display this information on a Venn diagram and then calculate the probability that a student studies both, studies at least one, etc., etc. Okay, hence, let's talk about hence. This is a keyword. I've already talked about it a few times. This means use your answer from before. So really, they're saying make the Venn diagram and then use it to solve these following questions. Now here's my big hint for questions like this. Use variables to represent the unknown values of the Venn diagram. Watch how I do this. So I have my two events, right? I have students studying physics, I'm going to use P. Students studying chemistry, I have C. So I know there's a number that goes here, here, and here. So I'm going to label this number A, B, C, and I actually need to know how many are not in either, so that's D. Now, what I'm going to do is take all of the numbers I've been given and use the variables to express them. So for example, number 19. This is the students who study physics. Well, all of these students study physics in this circle. So that's all of these students, A plus B. 17 study chemistry. Okay, well that means it's B plus C. Remember, B is the students who study both. C is the students who study only chemistry. But if I'm saying students who study chemistry, I'm talking about all of them. 15 study both. Well, both would be, oh, these students B. And the last number we were given was 30. That's the total number of students. So that would be A plus B plus C plus D should give me 30. Okay, I'm going to solve, what I have now is 4 equations and 4 unknowns. But they're not difficult equations. So I'm going to solve this, but I'm going to solve by inspection, meaning you don't need to do a whole, sub 1 into 2, sub 2 into 3, because you can kind of figure it out pretty quick. First of all, we know that B is equal to 15. That was given to us. If I subbed B into the second equation, if it's 15, so that means C has to be 2. If I sub B, which is 15, into the first equation, then if 19 equals A plus 15, so A has to equal 4. And then if I sub all of them into the fourth equation, so I have 15 plus 19, 21, so this is going to be D is equal to 9. So that's what I mean by solving by inspection. So now I've solved my Venn diagram. I know the numbers. This is 4, this is 15, this is 2, and this is 9. Now, maybe you could have filled in the Venn diagram without doing this strategy, and that's fine. If you can do it carefully and get it done without my this method, that's okay. This method is very robust, so it always works. If you're ever confused or if you're worried you might make a mistake, this is a reliable way. That's what I mean by robust. So you can choose to do what you like, but if you don't use this method, there is a possibility you could get confused or kind of interpret the numbers wrong. Okay, so now we use my Venn diagram. Find the probability that a randomly selected student studies both subjects. So I want to find the probability that a student studies both. Okay, now we're looking for a probability, not the number of students. So really what we want is the number of students that studies both over the total number of students. So that is 15 students study both over 30. Look how quick that was. Just read it right off of my Venn diagram. Part B, the probability that a student studies at least one of the subjects. Okay, well the probability of studying at least one, that would be, that would be this student, they study physics, 15 study both, and 2 study just chemistry. So it'd be all of those students would be valid, 4 plus 15 plus 2 over 30. That gives me 21 over 30. Okay, next question. The number of students who study physics but not chemistry, again, I can see it right there. There's the 4 students, but I have to express it as a probability. That's the probability of P but not C. That's 4 over 30. Now remember what I told you. All I want you to do is give me the final answer. You don't have to round it, or so you don't have to reduce it, and you don't have to convert it to a decimal. I don't want you to get caught up in notation, but let's just show you the notation so that we can kind of tie this all together. This is the probability that you study both. So that would be just these guys here. That's the intersection. So this would be the probability of P and C. Intersect C. This one was the students that study at least one. So they study physics or chemistry or both. So that's a union of physics and chemistry. This one here is study physics but not chemistry. So that's this crescent moon section. that would be the probability of P and the complement of C. Remember, that's what we just did, right? The half moon is the first thing and the complement of the second thing. All the things that are both physics and not chemistry. Anyways, the question's not asking you for these notations. Don't get caught up in them. Don't worry, oh, I have to figure out this notation. All this question wants to know is the probability. Case in point D, which is the probability of student studies exactly one subject. So that would be these students and these students. So that would be the probability of exactly one is 4 plus 2 over 30, which is 6 over 30. Now, students always ask, well, what's the notation for that? This is where it gets so crazy, right? Because there's no way of doing this. This is the probability of P and not chemistry, so that's what we just found. That would be just P. Union with the ones that are just chemistry. So that'd be P complement intersect C, just C. So it'd be the union of the just P's and just C's. That's what they mean by don't get bogged down in the notation. Right? This question, if you worried about writing perfect notation, you would spend your whole day worrying about that and you wouldn't get the right answer. So don't get bogged down by notation. Just write numbers. Okay, and finally, last question. What's the probability a student studies neither? Well, the probability of neither are the students that aren't in either circle. We found that there were 9 of them, so 9 out of 30. Again, the notation we looked at on the back, this could be the probability of P union C, but the complement, or the probability of being P complement and C complement. Okay, so you're going to get questions like this. This is a reliable way to solve them. Solve the Venn diagram, then fill in your probabilities. Your homework is page 71, number 1 to 6. Good luck with that, and we will see you next time.